So to achieve resonance, you want to have the voltage across the resistor, and you want to have the voltage across the inductor and the voltage across the capacitor to be equal and opposite. So you really want your VL to be equal to your VC, and you can adjust that frequency. So if we have a wee think first about how the impedance of your inductor and your capacitor change with frequency. So say we said this was your increase in the frequency, this was your value of XL, this was your value of XC. And you know the formula for XL equals 2 pi FL. So what happens to XL as you increase the frequency? Right, so if you had a frequency of 0, your XL would be 0, wouldn't it?
Yeah.
And then as you increase your frequency, your XL is going to keep increasing. Now, it would be a directly proportional relationship, wouldn't it? So it would be a straight line. It would go like that. So as your frequency increases, your XL must increase. It's a directly proportional relationship. XC's got a different formula. XC is 1 over 2 pi FC. So what happens to XC as F increases? It would decrease, but it kind of decreases in a kind of exponential way, so it kind of, this will never kind of hit that curve. So it will kind of come down, kind of like that. At the point where you hit resonance, as in VL is equal to VC, your impedance has to be equal and opposite. So you're looking probably on mine, and I'm going to be equal and opposite about there. So at that point, I would say my XL and my XC are equal, and that must be my resonant frequency, my FR. So that would be at resonance there. If you're drawing that in a phasor diagram, as in just on the cross, then on an impedance phasor diagram, that would be my XL, that would be my XC, and my value of resistor, remember resistance isn't dependent on frequency at all, resistance just stays the same, would remain the same. So from that you would determine that at resonance the impedance in the circuit is equal to the resistance. And it's at resonance in this type of circuit. So that's the value at resonance. And in terms of the impedance in this circuit, because these are equal and opposite, you can't have any more. That's the kind of lowest value of resistance or impedance you could have in this circuit. If you added in a bit of XL, you would increase that and you'd get a hypotenuse, which would be larger. So that is the circuit's at its minimum value of impedance. Now if you've got a minimum impedance, what do you have in terms of current? So you'll have a higher current. So you'd have a maximum current. So if you've got a minimum impedance, then that will draw a maximum current. So that's why you use these types of circuits as filters. Because what you would have is you would have a maximum current that can pass through, and then at all these other frequencies, everything else would be diminished. So you'd get a big oscillation or a big current at a particular frequency. And when you liken that to mechanical systems at resonance, then you're likening it things to like bridges that oscillate and all that kind of thing. Have you heard of bridges that oscillate, they get problems, they have to be rebuilt? Or wine glasses shattering because if somebody, an opera singer, sings to a wine glass, the wine glass vibrates and it shatters. So if they can turn a small oscillation or a small current or a small whatever it is into something much bigger using resonance, then that's what you achieve. In electrical terms, it's just filters basically to let things pass by. And in mechanical terms, it'll be things actually oscillating and vibrating, things that you see. Okay? So I'm going to give you notes about resonance now. So in your notes, this is something that you never have to remember. You have given to you, on the basis of, at resonance, XL equals XC, you have the proof there on page 8 for how you get from XL equals XC to how you actually get the resonant frequency. You don't have to be able to replicate doing this proof. This proof is just here to show you how they've come to that conclusion. But this is the formula that you would use to determine the resonant frequency. So that's a formula that you kind of need to use. So I'll pop that onto the bottom of the page. Also, you have that the impedance at resonance is equal to the resistance. We've already got that. The impedance is equal to the resistance. The phase angle will be 0. You can see that. Oh, and also when they talk about resistance, when it's resistance at resonance, they call it dynamic impedance or dynamic resistance. So instead of it just being R, it'll be RD. But it is just the resistance in the circuit. Then the other thing they show you are the graphs, which are kind of what we've just talked about. So you see the graph here, this one that kind of swoops through here. This is your impedance as you go near resonance, dipping down. So at your minimum value when your Z equals R, and then you've got your current coming up. Now, this one is very narrow. They're not all that narrow. So you'll get all shapes and sizes if you like, but it will show you minimums and maximums. The minimum can be sharp and the maximum can be wide or vice versa. But they won't all look exactly like that. But there'll be that idea where you hit maximums and minimums at resonance. Then you have a thing, Q factor, which is about voltage magnification factor. Now, the values that I chose gave you a small XL and a small XC. So they would give you bigger voltages. So you can theoretically have, let's have a wee look. Turn it off. You could have a resonant circuit. And say that was 200 volts AC at some frequency that's resonant, we don't know. And you could have, that's your R, your L, your C. The voltage across your resistor would be your 200 volts. It would be that voltage there. Your voltage across your inductor could be far higher or far lower than that. That could be 500 volts. If that's 500 volts, that must also be 500 volts. Because on your phasor diagram, that would be your VL, that would be your VC, equal and opposite, cancelling each other out. That would be your VR, which would be equal to your VS. So you can have massive voltage magnification. So when you're doing your resonant calculations, you can work out, you get big massive voltages across your inductor and your capacitor that are far larger than your supply voltage. They're not wrong, they're just equal and opposite. So you can end up with one of the problems of resonance is you've got massive voltage magnification. So you do get voltage magnification, that's one of the things. And then the last thing you really get that's spoken about is the Q factor. So it tells you on page 11 of your notes that resonant circuits respond to frequencies close to their own natural frequency much stronger than they respond to other frequencies. And that ratio is a measure of the quality of the resonant circuit, or how well it resonates. And your formula for your quality, your Q factor, is that formula there. Again, to give you the proof, you would never have to work that out. So I'm going to add that in. All based on the values in the circuit. So no complex numbers for this, you'll notice. And the last thing you should have is your bandwidth. So your bandwidth is worked out by looking at your maximums and looking at 0.707 of that maximum. Looking at the before point, the after point, and how wide that is. So that'll give you how sharply that resonates. And to get the bandwidth, that's the formula there. Gets you the FR over Q. And they are really the key concepts and the key formulas that you need for this wee section. So what I'd like you to do now is self-assessment question 1 on page 15.